or why do you stress on this? We stress on this because we are going to deal with the solution of system of linear equations, and often the solution it will be a one-dimensional structure or one-dimensional space. So the solution can be a line, or the solution can be a plane. And this, we call it a space because often the solution space, they have several definitions, and you might get confused, but you should not. For example, we have a system of equations that can look like this: ax equal to 0. Okay, so this is a system of equations where the coefficient matrix is in A, the unknown values are in x, and we get a 0. And the solution here, this x constitutes the null space of A, okay? Null space of matrix A, or we can denote it like NA, sorry, how do I write this one? NA, yeah, I think this is enough. Null space of A. So now when you hear the null space of A, don't be afraid, okay? What null space is in fact the equation of a line, okay? Or it is the equation of a plane. So this is the null space. Or we can also have the following. Let's assume that we have 2x plus y, this is equal to 3, and 5x minus y is equal to 4. Okay? So this is a system of equations. Let's try to find the solution. What is the solution here? We can, so having this, we can obtain the following. We can add two equations. We can get 7x is equal to 7, right? If we add these two, minus y plus y, they cancel each other. So we get x is equal to 1. We substitute x here, we find that y is equal to 1. Okay, that's good. So this is a space, the solution space, okay, which is just a point. Dimension is 0. So, but it could be a line where the dimension is going to be 1, or a plane. But this is the general definition of what we call a space. So that's why I just want you to remember how these equations look like. Even if you don't remember, don't worry. Whenever we solve the examples where the solution will be a space, we'll try to be as clear as possible for you. So let's erase this part here. Let's remember what these were. And now let's talk about a new topic. It will be system of linear equations. Now, let's assume for a moment that we have an equation that looks like this. Let's say we have a11x plus a12y plus a13z. This is equal to b1. If you look at this equation, what does this look like? What is this equation? Any comment?
Three-dimensional.
Yeah, there are three variables.
There are three variables, okay. And this is a structure of how many dimensions?
Dimensions in space.
Actually, it's
2 dimension.
Why?
It's a plane.
That's correct. So it's 2-dimensional, it's a plane, okay? This is the plane.
And it's the Cartesian equation of the plane.
Okay, this is the equation of the plane. Why? Because we used to see, actually, let's give an example. Let's assume that A11, A12, and A13, let's give some random numbers. Okay, let these numbers be the following. Let's say 3x minus y plus 5z. This is equal to, give me a random number, 2. Let's write this 2, okay? Then this is the equation of the plane, because we can write this one. This is also the equation of the plane. Inner product of n and x. This is equal to 2, okay? This is equivalent to this. So don't forget, if you go back to the notes of the last session, we are going to see that this was also the equation of a plane. What is n? Can you help me here? What is n?
Is a normal vector, let's say, or 3 minus 1, 5.
Exactly. So this n is the normal vector to the plane. So in the plane it looks like this. The normal is this one, and we read it from these coefficients. Okay. So please, we're also doing a small review. So what is x? X is x, y, z. Okay, and the inner product of these, what is the inner product of nx? Reminder from the previous week material, this is equal to n transpose times x. Okay, they are both vectors now. What is n transpose here? N transpose, that is 3 by 1, and this is 3 by 1. N transpose, it becomes 1 by 3. So we write this one 3 minus 1, 5. This is 1 by 3. We multiply this one with x, y, and z, which is 3 by 1. And the multiplication of a matrix, which is 1 by 3, with a matrix which is 3 by 1, it is just a number. Okay, it's 1 by 1. So in this case, how do we multiply these? This is 3x minus y plus 5z is equal to 2. This is what we get. Good. So apparently, this is the equation of a plane. Okay, and the equation of a plane, let's not forget, it's either this one, okay, or this one, which is equivalent. But this, writing this way, it's in the Cartesian form of representing the relationships between the three variables. But this and this, they are equivalent to this. Okay. So this equation of the plane, it is, they are all equivalent. But now, what we did in the last 2 minutes, we also did a small review of how the planes look like. And you remembered yourself, you said that you can read the normal value from here. Good. Now we also brought back the idea of what planes look like. And just for a moment, let's assume that this plane here, the equation of this plane, it is extended in space something like this. Okay, let's assume that this is the plane, the first plane. Let's give another equation which looks like this: a21x plus a22y plus a23z is equal to b2. Okay, so this is also a plane, right? So this is also a plane, and we can show this plane like this, extends like this. Okay. And they intersect together with this other plane. And what is the intersection between two planes?
A line.
That's correct. So intersection between two planes is a line. And you are electronic engineering. When you are going to, when you will be in the second year, you are going to study Cartesian, cylindrical, and spherical coordinate system. And you are going to have intersections of three planes in three different coordinate systems, in three different orthogonal coordinate systems. And what you learn here, which you are smart students, and of course, even just by intuition, you can pick it up easily. But you're going to see it then, again, in, let's say, in spherical coordinate system, you'll have the intersection of three planes to define a point. So far, you said that this is a plane, this is a plane. I want x, y, and z to be both in this plane and this plane, which is going to define probably a line that looks like this. Okay? Then we can provide a third plane. Now you know that this is the third plane. This is A31, A32, A33 is equal to B3. Okay? So we don't even need to write these actually, so it might be a waste of time because we know what they are going to be. Okay? But let's write the X, Y, Z. Now we bring in a third plane, which is going to extend over some space. And now, what is the intersection of a line and another plane? This can produce a point. Okay, so we have the intersection of two planes that might look like this. Okay, so they intersect. They make a line, so you can see where the line is. And then you can have another plane which is approaching from a different angle. And these can clearly define a point. So here in this system, we see that we have three equations of three planes. We can generalize this one in a larger how can I say, number of variables. So we can have spaces in 5-dimensional space. If it is 5-dimensional space, it's a plane of a different nature, which we cannot visualize it very easy. But let's approach to our problem step by step. So here we have here we have three equations. Now these three equations, you can see that there is a lot of repetition. When you say repetition, we have x, y, z. Why would you write them each time? They are the same thing. Rather than this, we can do it like this. We can say we can write just the coefficient values A11, A12, A13, A21, A22, A23, A31, A32, A33. Then we multiply these with these variables, which are, we can even not forget, we can keep them out, and we can write the following. This is equal to B1, B2, B3. So with this here, we call this one, this is the coefficient matrix. This is the matrix that carries the coefficients of all of these elements. This B, this is the answer. This is the unknown vector. This is the unknown vector. Now, this whole system here, we can write it like this. We can write that A, this is the matrix A, and this A, in this time, this is 3 by 3, okay? And X is a vector which has a dimension of 3 by 1, and this is equal, what is this equal to? What is the dimension of the answer of this product? It is 3 by 1, okay? Now here, this is the general expression of a system of linear equations. So this topic that we are going to cover today, system of linear equations, this is how we write it. Now, we can write down an example, which could be the following. Let's assume we have x1 plus x2, we have x1 plus x2 plus x3 plus x4 plus x5. This is equal to 3. Then we can have 2, 1, 1, 2. Okay, so we can have here 2x1 plus x2 plus x3 plus x4 plus 2x5. This is equal to 4. Then we have x1 minus x2 minus x3 minus x4. So we have 1 minus 1 minus 1, 1, 1. x1 minus x2 minus x3 plus x4 plus x5 plus x4 plus x5. This is equal to 5. Okay, so here we have, so how many equations do we have so far? How many equations do we have on the board?
3 so far.
3, so this is the fourth. How many unknown variables do we have?
5.
5, that's true. So we have 5, which means that
We need 5 unique equations.
we need 5. Why do we need 5? So this x, you are saying is 5 by 1. And this coefficient matrix A, what could be this coefficient matrix A? What can we write over there? This is 4 by 5, okay? We have 4 rows and 5 columns in here, and the answer is going to be 4 by 1, okay? You said that we need 5 equations in order to do what?
In order to find all of the variables' values.
Okay, so please don't forget this one. All of you remember this one. So we said that apparently we have 5 unknowns, and we need 5 equations. Okay, now, but how should these equations, how they should be? How should these equations be? That's one question.
I think they should be unique, so we shouldn't have redundancy between the equations.
Okay, yeah, that's a good word. You are saying unique, or we could also use another term, which is linearly independent.
Yes.
Linearly independent, this means that we should not have one equation which looks like this. Let's say 2x plus y, this is equal to 4, and 4x plus 2y, this is equal to 8. What do you see in these two equations?
It's the same equation. It's just by a factor of 2.
That's correct. So we cannot find, so we have only one equation because this one multiplied by 2, you get this. This is not telling anything new. So that's true. These two equations, so this is, we cancel this out. These are called linearly dependent. Linearly dependent. Now, in order to have, if we have 5 unknowns, we need 5 equations which are linearly independent, or you use the keyword which was unique. Okay. Now, let's try to simplify this system of equations, or let's write this in a more elegant way. So here we have some information which, if the equations, if they look like this, let's have a look for a moment, it is easy for a human eye to detect that there is a linear dependence. Here, we could have some dependencies, but it's hard for us to see whether there is any relationship between these here. Let's watch for a moment. So, in fact, if we add the second equation and the third, if we see these, they will be cancelled out, okay? Because this is plus, plus, minus, minus. So we can have 3x1 plus 2x4 plus 3x5 is equal to 9, okay? So here we have one essential information. Actually, if you look at this one, if we add the first and the third, what do we get? It's not our objective to do it, but...
We get the fourth.
Say it again?
I think we get the fourth equation.
Do we? Or if we have this one and this one?
Actually, if you look at the numbers.
Yeah, you are right. We get, if we have the first and the third, imagine, if you have, before solving it, if you spend 1 minute just by looking at roughly. So first plus third, what do we get? First and third, we get 2x1 plus 2x1 plus 2x4 plus 2x5. This is equal to what? What is, when you add the first equation and the third?
8.
8, that's correct, 8. Now you cancel 2's everywhere, and it looks like this is the fourth equation. So it looks like we have 5 unknowns and 4 equations, but really, it's not really 4 equations. So this was your suggestion, right? You said that 5 unknowns, we need 5 equations, but the real issue here is that we have 5 unknowns. We have 4 equations, but using a very intuitive and very fast analysis, this is not really 4 equations, okay? Apparently it's 3 equations. So this is what we have here. Why? Because the fourth one, it can be described as a linear combination of 2 others, which means that this is not telling any new information, okay? So whenever you are discussing something, you call someone and say, tell me something I don't know. And people are generally, they offer to you some general information. You say, I'm not learning anything new. Tell me something I don't know. And this will tell us to equation 4. It says, well, x1 plus x4 plus x5 is equal to 4. We say, I already know it. So stay away. Okay, so we can take it away. But let's try to see how we can observe this dependence of equation 4 with the first and the third. Let's see how we can extract it otherwise, or in a different method. So let's write the coefficient matrix. Here we have 1, 1, 1, 1, 1. Then we have 2, one, 2. This is the second equation, the coefficients. Then for the third one, we have 1, minus 1, minus 1, 1, 1. We have 1, minus 1, minus 1, 1, 1. The last equation we have here 1, 0, 0, 1, 1. So this is the coefficient matrix. Whenever we have this coefficient matrix, we try to use a term which we call the augmented matrix. So for example, if we have here AX is equal to B, let me say, wait a second, so we can augment, we have, so how many rows does A have?
4.
4. That's good. How many rows does B have?
4.
4. Good. Now, since A and B, they have 4 rows each, we can merge them together. When we say merge, we can put them like this. Because let's assume for a moment that B had only 3 values. Let's assume that we have this system of equations, okay? Can we merge some elements that are going to look like this? 2 minus 3, 7. Can we merge these values with this matrix? No, because the matrix would be something like this. We don't have a matrix that is going to look like this, okay? This is never possible. So this is essential because, for example, in more advanced courses, in deep learning, there are some algorithms where you have a data set, but you try to modify during the way. And sometimes it is very useful to concatenate or to merge 2 different matrices. But the user has to be careful so that at least one dimension of the matrix should be the same. In the first week, we said that when you add 2 matrices, they should be the same dimension. So a matrix which is 4 by 5, you cannot add it to a matrix which is 3 by 5. Okay? The same way, we can merge only matrices which have the same number of rows. So for example, this never works. This is stupid. You cannot show to someone a matrix like this. But here we observe that B has 4 rows. You see here, A has 4 rows. So we can merge them. We can bring closer these values. We can write here 3, 4, 5, and 4. Okay. And we have this new matrix, and this new matrix, which is composed because of from A and B, we call this one augmented matrix. Augmented matrix. So always, when we solve a system of linear equations that is stated here, it looks like this or like this. The first thing we construct is the augmented matrix, and it's going to look like this. Then we follow a series of procedures or a series of steps that we need to carry out. These series of steps are the following. So we'll try to write them down here on the board, and they're going to look like, so the first step is that we construct, well, we don't need to write this one anyway, but we construct the augmented matrix AB. Second, identify the pivot row. Pivot row is a reference row. So we're going to use one of the rows here. So this is the first row, this is the second row, third row, and fourth row. We're going to select one of those as a pivot row, and from the pivot row, we're going to select the pivot element. A pivot element, but pivot element, they have to be +1. Okay? So a pivot element is going to be normally the leading number. So we want it to be +1. Then the third step is so here we can set get reduced row echelon form. I'm going to write this one. Row RREF. I'm going to write this one just for a moment. So we construct the augmented matrix, and we need to get reduced row echelon form. We identify the pivot row and pivot element, and then we use these equations, which is going to look like this. Rj star is equal to Rj minus Ri. The way to read this is that the new value of a specific row is going to be equal to the value of this row minus a constant lambda times Ri. And j is larger than I. What does this mean? This means that we can say that the third row can be written as the values of the third row minus the values of the first row. Okay, so this is what this is going to look like. Okay, so we can use the first row as a pivot or as a reference for second, third, and fourth, meaning that we can change the values of row 2, 3, 4 using row 1, and you can change the values of row 3 and 4 using row 2. Okay, we can change the values of row 4 using row 3, row 2, or row 1. So we follow these operations, and once we do this, we try to make or produce sparse matrix. Sparse matrix is a matrix which is full of zeros, okay? So there are many researchers around the world that their research or what they work on is sparse matrices. And these are matrices which have a lot of zeros, okay? So we try to simplify the expression. So if we have something like this, like let's say x1 plus 0, x2 plus 0, x3 plus x4 plus x5, we simply write it like this, okay? So that we try to extract as much zero as possible to simplify our problem. So we try to produce sparse matrices, and once we do it, you get reduced row echelon form. Now let's move with the. Let's try to solve this system of equations. So this information, we can take this out, and let's check here. So first thing, which one is a pivot row? We can use the first row as a pivot. So let's write here R1. We can use this as a pivot.
Professor, what do you mean with pivot?
Pivot is a reference row. It's a row which you can use it to modify the other rows. Решти reference. Okay, it's a pivot row.
Okay.
And the objective is to make these elements. So here we have 1, 2, 3. Our objective is to make this full of zeros. Okay, and the next objective is to make also these all zeros. Okay, so we like to have only the diagonal term to survive. All the rest, we want to do these zeros and these, and we can do it. It is easy, okay? So, and let's see how we can do it. So initially, if we have row 1 as a pivot, we check whether this value is +1. Luckily for us, this is already +1, and the next step is that we want to make these zeros. So we start first by making zero, this, and this. So how can we do it? We can write the following. We can say that the row 2 star can be equal to row 2, then what? How can we make this 2 0 using this one? -2 row 1. Okay? We can write this down because we know that 2 minus twice of 1, we get 0, right? Then we have row 3 star, this is equal to row 3, then what? Okay. Then row 4 star, this is equal to row 4 minus row 1. Okay. So these are 3 equations that look like this, which are even here. Okay. And we use these to get zeros from here. So let's have a look at the first equation. We say that row 2 star is equal to row 2 minus 2 row 1. That's good. And how do we do it? Let's have a look for a moment. So what is row 2? Row 2 is 2, 1, 1, 1, 2, 4, right? So this is row 2. So I wrote here this row 2 minus 2 row 1. What is 2 row 1? You see where the row 1 is, and from here you subtract this row. We multiply by 2 all these elements, right? What is it? It's going to be 2, 2, 2, 2, 2, 2, and then what should we get here? So this is row 2 minus
8.
no, it's 6. We are subtracting twice row 1, right? Is it clear?
Yes.
Okay. So being a Friday makes us sleepy. So this is what we are writing here. So this is row 2 minus 2 row 1. So here we get the following. Okay, this is simply, let's not forget, this is 2 row 1. And we subtract these two together. We have 2 minus 2, 0, 1 minus 2, minus 1, 1 minus 2 minus 1, 1 minus 2 minus 1, 2 minus 2, 0, 4 minus 6 minus 2. Okay? So, do we agree here? So then, let's continue, or maybe we can continue right here. So the first row, it stays the same. The first row does not change. We get here 1, 1, 1, 1, 1. And then this is the element 3. So now the second row will be updated. We're going to write this one, okay? So here we get 0, 3 minus 1s, 1, 2, 3, 0 minus 2, 0 minus 2. Then we have to modify the third row here. What do we get for the third row? We have row 3 minus row 1, so it is going to be easy. We just subtract these. Who can help? Who can do this for me? What should we write here?
0.
Yes.
Minus 2.
Yes.
Minus 2.
Yes.
0.
Okay.
0.
Yes.
And 2.
Yes. 5 minus 3 we get a 2. Okay, thanks. Then the fourth row, it will be row 4 minus row 1. So what is this going to be?
0.
Yes.
Minus 1.
Yes.
Minus 1.
Okay.
0.
Yes.
0.
Yes.
1.
Okay, that's it. So we did it. So what we did this part, we tried to make it sparse, and now what is the next step? The next step is the following. So here, this was the pivot element. Now we need to we have to look at the second row, and we are going to use this one as a pivot, the Bordone tesserae reference. We're going to use this one. But for that one, we need the pivot element to be minus 1. How can we do it? In order to make this, so we have to change, we have to have this leading element plus 1. How can we do it? We can do the following. We can say that row 2 star, okay, this is going to be equal to minus 1 times row 2. We can do it, okay? Why can we do it? Let's see. Let's assume that we have 2x plus z, this is equal to 4, okay? Multiplied by minus 1, we can get the following. We can get minus 2x minus z, this is equal to minus 4. Are these two equivalent? Yes, they are. So here, similarly, we can change the sign here. So, because we need to make this plus 1. Then at this stage, if you allow me, I can change the signs of everything right here. And this becomes minus 1 times minus 1, we get 1. Minus 1 times minus 1, 1. Minus 1 times minus 1, 1, 2. Okay? So we updated the second row, and now that we updated it, the leading element is 1. What is the next objective? So we will... Yes, say it again.
It's the third row, so we multiply by minus 2.
Yes. So let's write this carefully. So using this one, we want to make these zeros. How can we do it? We could write these equations. So let's have a look. One final look here. So we can say that row 3 star, this can be equal to row 3, then what? How does this minus 2 become 0? Plus 2 row 2.
And we should add the fourth.
No, we can add twice row 2.
Multiply maybe the third row we multiply by itself, and we add like 4. No.
Well, what did you read this one? Can you read this on the board? So row 3 star, this is really convenient as row 3 plus 2 times row 2. Because we have to modify the third row using the second. So how can we make minus 2 0? You add 2, right?
Yes, yes.
And this, the 2, we get it from here. Then, so we fix it this way. What about row 4? How can we make this minus 1 0? We add 1. Would you agree? So we have a minus 1 here. You add 1 against 0. So this will be row 4 star. This is going to be row 4 plus row 2. Okay? So then let's move to the next step here. We write the first row without changing it. So we get 1, 1, 1, 1, 1. There is a 3 in the end. And then the second row, it doesn't change. This is 0, 1, 1, 1, 0, 2. Then, okay, now can someone help me with this? How can you apply that equation over there? Row 3 star is equal to row 3 plus twice row 2. What is this number going to be? So let's write it here. I want you to have a look at this one. So what does this equation say? It says row 3 plus 2 row 2. What is row 3? Let's write it here. I guess you cannot see this part. Now you do see. So what is row 3? It's 0 minus 2 minus 2, 0, minus 2, minus 2, 0, 0, 2, 0, 0, 2. Okay? So this is row 3. What is 2 times row 2? 2 times row 2, it is 0, 2, 2, 2, 0, 4, right? So we are subtracting, no, what are we doing? We're adding these two together. So what do we get here? We get 0, 0, 0, 2, 0, 6. Okay? So we get 0, 2 more zeros, 2, 0, 6. Okay? Then row 4, we add row 4 with row 2, so we read it from here. So we get 0, 0, 0, 0, we get another 0. What is next? Can someone help me here? Yes.
1.
And then? Yes.
0. And then
3. Okay. So now, what does the third row and the fourth row state? They state the same thing actually, okay? Because this is like an equation. If you multiply this by 2, you get this one. Okay? So at this stage, what we can do is the following. We can report, we can say, I think we remember when we did it like this. We said row 2, we multiplied it by minus 1. We can do it. So here, we can say the following. We can say row 3 is equal to row 3 divided by 2. Okay? If we do it, we make this 1 because we like to have leading ones, not to initiate. So we get 3. Okay? Then the next step is that we can do the following. We can do row 4.
So there is row 3 is equal with row 3 divided by 2.
You're right. Okay, this was a mistake. Sorry. Thank you for noticing that. So now we get this. Then we can say row 4 minus row 3. what do we get? All zeros, right? So the moment we get all zeros, we can conclude, now we can for sure say that we don't really have a fourth equation, but this is something that you notice it the first moment we write those on the board, right? Using the intuition, you figured out that the third equation is the first plus the third, and so on. So, okay, so we are at this point. Then, what do we always do? We always try to keep track of leading ones. Where are the leading ones? We find them here, here, and here, okay? And now, the objective is to make zeros anything below and above of leading ones, okay? So, you have a look at this one. These are all zeros. That's good. We have a look at this one. These are all zeros here. These are all zeros here. But we can use this one to produce a zero from here. Okay, we need to make this zero. And then here we cannot do much here. But we can use this other leading one to make a few zeros here. Okay, so this is going to be our next objective. So we have this equation. So what is going to be the next step? We can use row 3 as a pivot, okay? And let's make this 0. Here we can say that row 2 star is equal to row 2 minus row 3, okay? Why are we doing it? Because using this, we clear this out. Then, in order to clear this other one out, which is row 1, how do we do it? We say row 1 star, this is equal to row 1 minus row 3. Why are we using row 3 here? Because row 3 is now the pivot, okay? When we make zeros here, in this section above the diagonal, so diagonal Echelon, okay? So when we make zeros above the diagonal, we use the pivot, the lower rows, as pivot to make zeros above. But if we want to make zeros down below the diagonal, we use the higher rows as a pivot for the lower rows. So then, let's move fast here. So we said that we don't have the fourth equation, so let's just use 3. We say here this is 0, 0, 0, 1, 0, 3. And then row 2. What is row 2? Row 2 is 0, 1, 1, 0, 1, 1. Then we have 1 minus 1, 0. Then we have row 2 minus row 3. So this is 0 minus 0, 0. What is the next number? 2 minus 3 minus 1. Okay. Then we have row 1 minus row 3. So we subtract. So then row 1 minus row 3, we get 3 ones. 1, 1, 1. Then we have a 0. Okay. Then we have 1 minus 0, this is 1. And wait a second, no, yes. Then we have 3 minus 3, we get a 0. Okay. So again, it's always to keep track of what are the pivot elements. They are here, or we call these leading ones. Okay. So let me write it here. We always, and this one we can take it out.
Professor, by having to solve the equation, that is the main goal?
Say it again.
By creating, let's say, zeros, we can solve the equation. We can find, like, for example, x4.
Yes, we can find x4. And what is x4 so far?
Is equal to 3.
That's correct. So far, we know precisely what is one of the unknown values without simplifying it.
This is the aim.
Huh?
This is the aim, the purpose.
Yeah, this is it. Yeah, that's true. That's correct.
Okay.
Professor, so this procedure is called getting the reduced row echelon form of a matrix, right?
Yes, that's what we're trying to do. Yes, we're trying to get this.
Everything we have done so far is that.
Yes, it's
Okay.
yes. And look, I believe this is very intuitive, right? Huh? Don't say that I don't know how to find the reduced row echelon form because it doesn't look very calculus looking like structure. Okay, so it's. Would you agree with me? Say yes, come on, say yes, say yes. Come on.
I can't, really, I can't. Calculus is simpler. Maybe it's because I studied calculus before, but maybe. I don't know.
Okay. I think it's because of that. Otherwise, this would be much more easier. But what is the most difficult thing you have done so far? Like 2 minus 2 is equal to 0? Huh?
Well, yeah, it's just simple addition and subtraction, but still, it's new, that's why.
It's new. Come on, man. I mean,
it needs some time to be internalized.
Okay, I can give you 1 minute. I can give you 1 minute. I can give you some time. If you need more time to do 2 minus 2 is equal to 0. Okay. Yeah. So, yeah. So then these are the leading ones. Maybe I need to write here a key element, which is this is very essential. Leading ones. Okay, then we move here. So we use this leading one to make zeros. Let's use this leading one to produce a 0 out of here. So how can we do it? We can do the following. We can say row 1 star. This is equal to row 1 minus row 2. Okay, row 1 minus row 2.
We can see there. We can see there.
Can see? Make it.
Now
Okay.
yes.
I can see Russia from here. It said someone a few years ago. Okay, so let's see. So we get in finally we get 3 zeros, 1 0 3, 1 2 3, 1 0 3. Imagine, yeah, this is what you have to be careful in linear algebra so far. So you have row 1 minus row 2. So here we get the 1, 1 minus 1, 0, and then we have what is left, 1 minus 1, 0 again. 0 minus 0, this is 0. 1 minus 0, 0. Then 0 minus 1, 0 minus 1 we get 1. Okay, is this all? Wait a second. No, we should have another 1 here. This is also 1. Does it look correct?
Yes.
Okay, if that is correct, then can you identify once again the leading ones? So here, the leading ones, we have them. This is this one, and this one. And let's not forget that these are the coefficients of 5 values, and these values are x1, x2, x3, x4, and x5. Okay, let's not forget this. So we can separate it like this. And then the question is the following. Which ones are leading ones? Which variables have leading ones? x1 has a leading one, okay. x2 has a leading one, would you agree? And x4 has a leading one. So this is the first essential information that we need to keep note. Then, which one have non-leading ones? Which variables? That's from x3 and
X5.
x5. Okay. So now what we do here is the following. So this was the procedure. So since x3 and x5 don't have a leading one, we call these free variable. Okay. So we can call this free variable. So what is a free variable? Let's write it, allow me to take out this part. So this was the procedure. I think we covered the relevant steps, but let's write x3 as a free variable. We say x3 is equal to s and x5 is equal to t. Now here s and t, they are real numbers. which means that they can be any number from minus infinity to plus infinity, and they can include also the 0. Now, then I can ask help from you to read for me the first equation. What does the first equation read?
It's x1 plus x5
Yes.
equals to 1.
That's true. What is the next equation?
x2
Yes.
plus x3 equals to minus 1.
Yes. What else?
And x4 equals to 3.
Yes. Now, let's compare this set of equations that we started with. Let's not forget, we started with this set of equations, which were 4 of those, okay? And it looks like these equations that are here, they are equivalent to these 3 equations, okay? Now, it is obvious that this new representation is way simpler, and we even have one value which is out there, which is 3. It's a fixed point, okay? Now, we wrote these equations, and we noticed that 2 variables, they were free variables. So, if you allow me, we can write here x1 is equal to 1 minus t. Would you agree with this? Because x1 is 1 minus x5, right? x5 is t, so I get this. x2 is equal to minus 1 minus s. Would you agree with this? Yes or no?
Yes.
Yes, okay, because we have, these are free variables and we wrote them as s and t. They are constant values. Not constant, so they are variable. They go from minus infinity to infinity, so this is what they are. And now we have, okay, so this is x1, x2, then x3, what is x3? x3 is equal to s, okay, what is x4? Is equal to 3, what is x5? Is equal to t, okay? So, these are the equations. Then, as a result, we can also immediately write the following. So, let's write them like this. We have x1, x2, x3, x4, and x5. This is a vector which we have to define, and we can write it in this form, plus okay. So what is x1? x1 is 1 minus t, right? 1, 0, minus 1. Would you agree here?
Yes.
Okay, thanks. So this is all. We solved this problem. And what does this solution look like? What is this solution here?
Intersection.
What space, what dimensional space is it?
5-dimensional, let's say.
No, it is not. But we wrote it on the board when we started the class today.
2-dimensional.
Yes. How do we... It's a plane, that's correct. So it's a plane. Then it is a plane, but we have not written all of it, okay? But you can distinguish it from now what it's going to be. What is x2? Let's write x2 here.
-1, 0.
That's correct, okay. What is x3?
0, 1, 0.
That's true. What is x4?
3, 0, 0.
Yes, that's correct. What is x5?
0, 0, 1.
That's correct, okay. So this is the answer. And now this answer, actually, this is a 5-dimensional plane. Sorry, 5-dimensional space. But the solution, it is a plane which is lying in the 5-dimensional space, okay? And this plane, we can we can write it like this. So X, the solution space, is equal to P, where we have this constant vector, plus S V plus T W. So this is a plane, okay? You know what an equation of a plane looks. And the solution here is, so let's notice for a moment. What was the coefficient matrix? It was A4 by 5, right? Okay. What does this mean? This means that we have 4 equations, right? We have 4 equations. How many unknowns did we have? 5 unknowns, right? This is the initial unknowns. So we started with 4 equations, 5 unknowns, but actually this was not 4 equations, it was 3. Okay? Then what happens is the following. We find that the dimension of the solution, let me write it like this. This should be larger, I don't know, let me think. This is the number of unknowns, where A is n by n, okay? N by n. So apparently this is n minus m, and this could have been 1, but is larger, okay? So this is larger or equal than this. Okay, so we have 5 unknowns, 4 equations. We subtract it, we get 1. So the chances, if 4 equations are linearly independent, we should get a solution aligned. But one of the equations was dependent on the others. So realistically, we have 5 minus 3, we get 2. So the dimension of the solution space is a 2-dimensional space. Okay. So here we said the following: dimension of the solution space is larger or equal than n, which was 5 minus 4. Okay. In fact, we got 2. So 2 is larger or equal than 1. So is it clear? So from here, we try to understand how the solution space can be a function, or the dimension of the solution space can depend on the number of unknowns and the number of equations. Okay, you have any question? Okay, then I can ask you, would you like to have a break or we continue?
Continue better.
Okay, so this was one essential, or let's say relevant equation or system of equations where the solution space ended up into being 2-dimensional. Now let's try to see other examples. Okay, so here we had one essential. So actually, let me ask you also this question. This system of linear equations, the system of linear equation, it is consistent if it has one solution. If it has at least one solution, it is consistent. So the equation that we just saw, how many solutions did it have?
Just a plane.
But what is the number of solutions? How many points are there in a plane?
Infinite.
Infinite. Okay, so it is consistent, and we can have infinite number of solutions. It is possible. We just saw it. It can also be inconsistent, and being inconsistent, that means that we have no solution. So it could be a system of equations which simply has no solutions at all. Okay, this is a possibility among many. So, and let's see, let's assume that we have a matrix which looks like this: 1, 2, 1, 1, 1 minus 1, 1, 1, 2, and the B it's 3, 4, 5, 3, 4, 5. So let's solve the system of equations and let's see. So first of all, how many equations do we have here? We have 3 equations, right? How many unknowns? Three unknowns, because this is 3 by 3, okay? And let's make the augmented matrix. What will be the augmented matrix? Augmented matrix will be the following: 1, 1, 1, 3, 2, 1, 1, 4, 1 minus 1, 2, 5. What was our initial consideration? The first consideration, it was to identify a pivot row, and then to check whether the pivot row has a leading one. Here, we have a leading one. Then what will be the next equation? The next equation, it will be row 2 star would be equal to row 2, then what? So we know that we want to make this 0, right? So what are we going to get then? Can somebody help me here? So let's not forget, row 1 is a pivot row now. So row 1p. So to make this 0, we have row 2 minus 2 row 1. Row 3 star, this is equal to row 3 minus row 1. And then what we get is the following. This stays the same, 1, 1, 1, 3. Then we have 2 minus 2, 0, 1 minus 2 minus 1, 1 minus 2 minus 1, and 4 minus 6 minus 2. Okay? Then we subtract row 3 minus row 1, so we get 1 minus 1, 0, minus 1 minus 1 minus 2, 2 minus 2, 0, 5 minus 6 minus 1. Okay? Then the next step is the following. Which one are the leading ones? We have this.
Professor.
Yes.
It is 2 minus 1.
Where is 2 minus 1?
At the last row you said 0 minus 2, 0, because you said 2 minus 2.
Yes, it's 1. That's true. Okay, this is 1. Then I made, okay, this is like this. You're correct, because when we do this, we just subtract the values without changing. I multiply the first row by 2. So this is 1 minus 1, 0, minus 1 minus 1 minus 2, 2 minus 1, 1, and 5 minus 3, 2. Okay, that's true. So then the next step, what we do is that we look whether we have a leading one in the second row. We don't have a leading one, so then what should we do? We can say that row 2 star, this is equal to minus 1 times row 2. Okay, which will make this one plus plus. Okay. So now that we have a leading one, we need to make this 0. How can we make this 0? We can write the following. We can say row 3 star is equal to row 3, then what?
Plus 2, row 2.
Plus 2 what?
Row 2.
Row 2. Okay, because row 2 is a pivot. So we should not forget. We should use row 2. And then, okay, this is all. So we can continue like this here. We can get 1, 1, 1, 3, 1, 1, 1, 3. We have 0, 1, 1, 2. And then we have row 3 plus 2, row 2. Okay, so this is 0. Minus 2 plus 2, 0. This is 1 plus 2, 3. And this is 2 plus twice this 1, 6. Okay, then what do we have to look for? we start to look for again what are the leading elements, leading ones. This is 1, this is not 1. What can we do here? We can divide by 3, right? If we divide by 3 here, we get here 1 and 2. Would you agree with that? So 3, 6, it becomes 1, 2. So here, this is a leading one now. Actually, at this stage, it looks like we found what is x3. x3 is equal to 2. So we have the answer. But now, we don't have a reduced row echelon form yet, because we made zeros down here. But we want to make also these zeros, which means that we have to make these zeros. Okay? How can we do it? We can use row 3 as a pivot row. So row 3 now, we say here row 3, it will be used as a pivot. And in order to do that, we can do the following. So how can we make this 0? We say row 2 star. This is equal to row 2, and then what?
Minus row 1.
No, minus row 3. Because to make zeros here above the diagonal, we need to use the lower matrices. Okay, so we should be careful about that. Then we have to make also this 0, where we have row 1 star. This is equal to row 1 minus row 3. And we move ahead and we write the pivot first. This is 0, 0, 1, and 2. And then we have 0 minus 0, 0, 1 minus 0, 1, 1 minus 1, 0, 2 minus 2, 0. Then, so what is x2? Apparently, x2, we can read it is 0. But let's see what is row 1 minus row 3. We just subtract these one by one, these pairs. 1 minus 0, 1, 1, sorry, 1 minus 0, 1. This is also 1. This is 0, and this is 1. Now, once we are done with all of these analysis, we immediately go back and check again the leading ones, okay? Here they are, here they are, here they are. Do we have above and below and above of everything? Do we have all zeros? No. We have this 1. We can make this 1 0, okay? How can we do it? We can write the following. We can say, now we have row 2 is a pivot, right? So here we have row 2 is the new pivot.
Professor, how do you determine which row is a pivot?
Well, we determine that with so if we are going to use this one to make zeros, this becomes a pivot, okay?
Oh, okay, so, okay.
So this is a row 2 pivot. So here, row 3 was a pivot because we want to make this one to make these zeros, okay? So if you want to make this 0, the only chance is to use this one. That's why we always try to circle. If you are in the exam, it will help you to determine all the time what are the pivots or the leading ones, because I deleted it now, okay? So this becomes a pivot, and then if this is a pivot, what is the equation we have to write down? We have row 1 star, because this is where we want to produce some zeros. Is equal to what? Can you help me with this one?
Row
1 minus row 2.
Row 2.
Okay. Row 1 minus row 2, that's correct. And let's do this here. So we have the row 3, it's 0, 0, 1, 2. Row 2, which is a pivot, is 0, 1, 0, 0. And row 1 minus row 2, we have to subtract, let's use a different color. So this is 1, 0, 0, 1. So what do we read from this system here? First of all, can we simplify this any further?
I think we have found all the variables or the unknowns.
That's true. So we cannot simplify it any further. Where are the leading ones? The leading ones are here, here, and here. Does this leading one has all 0 in its own column? Yes, in its own column, this leading one is everything else is 0. Let's check this leading one. Is this the only number in its own column? Is the rest all zeros? Yes, all the rest are zeros. Good. Also, what about this one? Are all the rest equal to 0? Yes, they are. So this is all we can do. So finally, we say that x1 is equal to 1. x2 is equal to what?
0.
Yes. What is x3?
2.
2. So what is the solution? The solution is one point, which is 1, 0, 2. Okay? It is not. So how many solutions do we have here? How many solutions did this system have?
Only 1 point.
Only 1 point, that's true. So it's a well-defined point. So far, we have seen systems that are consistent and have infinite number of solutions. We found that we had a plane as a solution. We can have one solution, but the question is, I can answer the following. Can a consistent system have 2 solutions? It's still a question. Can we have...
I don't think so, because since they are all equations of the first degree, they should have one solution, maybe.
That's a very good point. That's a very good point, because we know that you're right. Just as a reminder for the rest of the class, I guess 3x squared plus 5 equal to, I don't know, 0. This can have 2 solutions, right? Because this is square. And this is a polynomial. What is the order of this polynomial?
It's of the second degree.
Second degree, that's right. So we have two solutions. What about this? 4x to the power 5 plus 3x squared plus 5, this is equal to 0. What is the degree of this polynomial?
It's of the 5th degree.
That's right. So we expect 5 solutions, right? We expect 5 solutions. And then we have to find them, right? What about this equation? Z to the power 8, this is equal to 1. What is the degree of this polynomial?
I think it's of the 1st degree.
But this is Z to the power 8.
Yes, but you can take the 8th root, and that wouldn't change anything, because the 8th root of 1 is still 1.
Okay, but we can do the same here. I mean, we can also do this. X squared is equal to minus 5 over 3. X squared is equal to minus 5 over 3. Actually, can you find what are the roots of square root of minus 5 over 3?
No.
No,
it's on the imaginary number group.
That's correct. So we can find them on the imaginary numbers. It's not in the real number space. This has no solution. But the polynomials, they should always have the number of solutions equal to the number of the degree or of the order. So yes, for real number space, no, but we have 2 solutions in complex number space. Now here, this is a polynomial of 8th degree. We need 8 solutions. What are those?
There can be only ones, like 8.
Like what could be the roots? What can be a value of z such that will satisfy this equation?
1 and minus 1.
1.
Where are the other? Sorry, 1 minus 1. Where are the other 6 roots? Where are those? They are in the complex domain. They are imaginary numbers, right? They have to be there. In real number space, we have some intuition. We can pick them up. But the complex ones, they are a little difficult. And you should be able to find them in the complex number space. And it's not a difficult example. But at the same time, you made a good point. If it is a linear equation, we cannot have 2 roots, right? It should be a quadratic or cubic. But for sure, we are in the linear equations. But we are convinced that we can have one solution, which is this one. We are also convinced that we can have an infinite number of solutions. So why can't we have 2? So we have 1, and we have an infinite, which we cannot count. And are you excluding the possibility of having 2 solutions? Can you think about this one? What can you say about this?
Professor, I think because if we have 2 points, then it is a line, and we have infinite solutions.
That's a good approach, but it's by intuition. So you are saying that if you have 2 points, we can draw right? Okay. Do we have any other comments from the rest of the class?
I think, Professor, if there are 2 points, these points consist on a plane, and so the plane has infinite points that is the meaning that one solution are infinite.
Is this? Do you mean 1 or infinite?
I guess so.
Yeah. Okay. So far we have a proposal or suggestion that this is not possible. Okay, but let's see. This still stands like a question. But now let's move forward. So when we discuss the system of linear equations, we have let's assume one example, which could be so let's solve this system. How many unknowns do we have here?
3.
How many equations?
2.
2 equations. Okay. How many solutions can we have?
There can be an infinite number of solutions.
Why?
Because we don't have 3 unique or linearly independent equations. So let's say z can take up any value to satisfy x and y.
Okay, that's true. So once we have A, which is 2 by 3, 2, it is the number of equations. 3 is the number of unknowns. Okay, that's good. So then the dimension of the solution space, okay, dimension of the solution space, what did we say before? We said it's going to be larger or equal than 3 minus 2. But we wrote this one in the previous example, and we had a case where it was 5 minus 4, because we had 5 unknowns, 4 equations. We said that it's going to be larger than 1, right? And it ended up being 2, anyway. But then, okay, so we are saying that the dimension of the solution space, it can be larger or equal than 1. So it could even be a line. But if you look carefully to these equations, what do they represent? They represent planes, right?
Professor, I have a question.
Yes.
In these 2 equations, they're basically the same, but they give different results. One of them is 6, one of them is a 1. Is that possible?
I don't know. I think it can be very possible, of course. I mean, we can find numbers that can end up being 6. We can play it. So basically, these are planes. We can turn planet. So these are planes, and yeah. And let's think about this one. Let's think about this equation. Let's look at this system for a moment, okay? Does this system have a solution?
No.
Why? Let's try to draw the first equation. This is C equals to par. Epsilon runs into 6 of it. Okay, so the first equation, it looks like y is equal to x plus 1. What is x plus 1? X plus 1, it's, first of all, y is equal to x is a line like this, right? This is y is equal to x. Now, y is equal to x plus 1, it's a line that goes like this. Sorry, this was not perfect. Then what is the second equation? Second equation is y is equal to x plus 2. Would you agree? So the second equation is going to look like a line which is parallel to this. So do they ever intersect? No.
No, because they're parallel, because their slope is the same.
That's correct. So here we have no solution. Okay? Because the two solutions of the first one and the second one, they are parallel. They never intersect. So it's never possible to find x and y that satisfy this equation and x and y that satisfy this equation simultaneously. Okay, good. Now, let's go back to this now. We go one dimension higher. We are dealing with planes. What is the normal vector to the first plane? What is F?
1 minus 1, 2.
That's correct. 1 minus 1, 2. Now, let's assume this is this plane, and the normal is this. Okay? This is the normal to this plane. What is the normal vector to the second plane?
Is the same vector.
Is the same vector. So if this is the plane with that normal, now the other plane is going to be somewhere here with the same vector. What does this make them?
Parallel, let's say.
They're parallel. Do they ever intersect? Probably no. Do they ever intersect?
No.
Okay, no. We gotta know. So, yes, so here we have two planes that are parallel. We have no solution. Okay? We simply say no solution. So when we have no solution, we call the system inconsistent. Okay? So it is good to have a solution because then the problem becomes consistent. But it could be also that there is none. So apparently, so far, we are running the options of having a system of linear equations where we have no solution, we have one solution, or we have an infinite number of solutions. One of you in the class said that these two solutions can never be the case. We're going to study this one. Now, we have another, so that's good. We have let me see. So you are sure, okay, I need to also to come to another point. So I believe, most of you might confirm this one. I believe that this was a relatively good example to remind all of us that because we can easily perceive lines, that this had no solutions. Okay, so this was relatively easy. Allow me to erase this part. And then let me change this system slightly. Let me change this system of equation and let me write it like this. Plus 2z, this is equal to 0. And x minus y plus 2z, this is equal to 0. Does this system have a solution? This new system. I changed the b.
It has infinitely many solutions.
Oh, really? Okay. How is this possible?
Because
it's the same plane.
Yeah, it's the same, and you can take whatever value you want.
Well, I think you're right, actually, but I can ask you another question. So, can you give me what is the simplest solution to this system?
If all x, y, and z are equal to 0.
That's correct. We can call this trivial solution. Trivial solution is one where everything is 0. Okay, or it's an even easier to distinguish solution. So trivial solution is one where x, y, and z, which is the origin. Okay, the origin of the Cartesian coordinate system is the following: 0, 0, 0. This is the trivial solution. Okay, so it looks like by changing the b, okay, by changing this answer vector, le ta quajmë të bëm vektorin I përgjigjeve ose rezultateve nga 1 tan, që mban vlerën konstante. Pra y-z i kemi krah të majt, kurse përgjigjet vlerë numerike konstante I vendosim krah të djathtë. Okay, kjo është b-ja. Pra ne duke ndryshuar b, shkum nga no solution, we got an infinite number of solutions. Okay, but you also correctly identified or stated that x, y, z equal to 0 is a solution, which is a trivial solution. Now, we can define the following. If we have a system which is ax is equal to b, this equation, this is called non-homogeneous. non-homogeneous system of linear equations, okay? Then, if we have another equation which looks like this, ax is equal to 0. Okay, let the p vector be equal to 0. This one we call homogeneous system of linear equations, okay? So what makes it homogeneous is that the right-hand side is equal to 0. Now, the same terminology, we find it also in the differential equations. You have not done differential equations yet. You will in the second semester. But in differential equations, which you have this terminology that you see in calculus, it's going to be something like this. dy over dx plus 3y, this is equal to 4. And then we have dy over dx plus 4y, this is equal to 0. Now, this equation, this is called non-homogeneous because you have this term. And this equation, it is homogeneous because this is equal to 0. Okay? This can even be 4x. Okay? So this non-homogeneous is homogeneous. You're going to see this again when you see, you say, okay, we kind of remember something like this because the terminology, it is equivalent. Okay, so whenever you use some terminology in linear algebra, you can see it also in a couple of different other topics. So if you take a note of this, I can erase differential equations for now because it's early before you have to cover first derivatives. But let me say also something like this. That in this course, we are going to do differential equations. So in the first semester of your bachelor study program, you're going to solve very difficult differential equations. They are very difficult because they will be coupled. But it will be very easy for you because you are going to use linear algebra. Once you use linear algebra, things becomes much more easy. So, so you're lucky to take this course. So now let's have a look at this system here. We have a non-homogeneous system, which is this, and a homogeneous one, which is this. Now, let me ask you this. Is it possible, let me write it like this. Can this system of equation, can this system be inconsistent? Think about this one. Inconsistent. Which means that, is it possible that this system has no solution? Yes, no? To be inconsistent, this means that this system has no solution at all. Now,
I don't think so.
Why?
Because in this system, I guess there are numbers that you can tell, of course.
Let's think about this one. If we have ax is equal to 0, this equation, it does have a trivial solution, which is x is equal to 0. Okay? So the origin of the Cartesian coordinate system will always satisfy such a relationship. Because whatever the coefficients are, if you multiply all of these coefficients with 0, this will be equal to 0. So this homogeneous system of linear equations, it always has one solution. It has at least one solution. Okay? So it could be a plane, the solution could be a plane which is passing through the origin, or it could be a single point being the origin. Right? So we can answer this, you are right. This is a big no. Okay? So here we have that we have a non-homogeneous system and a homogeneous system. And in this case, we can say that the non-homogeneous system of equations can, in the general solution of such a system, it includes in itself the solution of the homogeneous system. Okay? So now, let's think for a moment. I specified this in verbally, but let's write it in such a way. So let's say, so we said that the general solution of this non-homogeneous equation, it includes this special solution of this homogeneous section. What do these two have in common? They have in common the coefficient matrix A. Now, if we have AX is equal to 0, the solution of this AX is equal to 0 is called the null space of A. Okay, we call this one null space. What does null mean in Albanian? What do you understand when you say null?
E zbrazët, bosh.
Është bosh, e zbrazët, shumë e drejtë, shumë e saktë. We call the null space of A, of matrix A. Or we can also call it kernel of A. Kernel of matrix A. So then the solution of AX is equal to B. It includes in itself the null space of A. So it is a space which is something like this. Imagine for a moment that the solution of X is equal to 0, maybe it's a line. But the solution of X is equal to B, maybe it's a plane which includes this line. Okay, so it could be a little more generalized, but it includes the original null space of A. So this is the null space of A, and then we can say that let's assume that Z is in LA, in the null space of A, and then P is a solution of AX is equal to B. Okay, so this is just one solution. Then the general solution of AX is equal to B, let's write it like this, general solution of AX is equal to B. It is equal to, so let's write it like this. So this general solution of AX is equal to B. It is equal to P plus all solutions of AX is equal to 0. Okay, so this is how we can read this, and probably we can write this a little better, which would be the following. But I guess for me, intuitively, when I see this, that's enough for me to remember. But in a more well-written way, we can say the following. For any vector x, such that this AX is equal to B is satisfied. So x is this. Okay? This x is going to be equal to the set of vector P plus Z. Okay? Such that Z is an element of null space of A. These two statements are equivalent to each other, okay? Now, let's assume that we want to determine the null space of a matrix. Let's pick up a 3 by 3 matrix. Can you give me some numbers? I can start with 1 minus 1, 2. Give me another row.
3 with 3 dimensions, Professor?
Yeah, 3 by 3.
3, 4, 5.
3, 4, 5, okay. And then?
And 4, 2, 0.
4, 2, 0, okay. 4, 2, 0. So this is a matrix, okay. We randomly wrote this down, and the question is, let's find null space of this matrix A. Or we can write it like this. So how do we do it? We construct, the first thing that we construct is that we construct the augmented matrix. What is the augmented matrix here? Allow me to do it here, right? See a augmented matrix. Vendosim bëra të krah. So what is B here? So this is A. I'm not erasing it, but I want to say that let's write what is A and B. What did we call this one? This was the augmented matrix, right?
Yes, always zero.
Thank you for confirming, but now you know that when we do elementary row operations, such as this one plus this one, or 2 times the row 1 plus row 3, what will happen with these zeros? They will remain zeros, okay? So probably we don't need to write these at all, because it will be redundancy of writing down zeros always. So we can find the null space of A, but not including these at all, at least at this stage. Would you agree? И що се коли ще душа треча ниша, кембуя, не до імбани, умежем зеро, психоскапутин, а не так противши?
Non dico in the prima.
Okay, confirm it, please. Don't waste our time. Do confirm it a little faster. So, yeah, let's keep it like this. So, these are kind of equivalent. So, let's do the task, the job that we do the best. First row is a pivot row. We want to make these zeros. How can we make these zeros? Who can help me here? What is row 2 star is equal to what? Row 2, use row 1 as a pivot.
-3 row 1.
Exactly, -3 row 1. What is then row 3 star would be equal to row 3, then what?
-4 row 1.
That's correct, -4 row 1. Let's see what we obtain. So we have 1, -1, 2. Then we have 3 minus 3, we get 0. Then we have 4 minus 3 times row 1. That means it's 7. We get here 7. Then we have 5 minus 6. We get -1. Okay. Then here we get row 3 minus 4 times row 1. So 4 minus 4, we made this 0. Then we have 2 minus plus 4, 2 plus 4, 6. And then we have 0 minus 4 times, so this is -8, I guess. -8. So what is the next step? The next step, so this is a leading one. We need to make here a leading one, 2. So how can we do this? This will be, we divide by 7, okay? We have to divide by 7. So this becomes 1, right? So this becomes 1. This is -1 over 7. Then what can we do this one? This is the pivot now. So we need to make the 6 0. How can we make the 6 0?
Sorry, Professor. You divided by 7, but would it be possible to subtract R3 from R2 to get a leading one? Because it was 7.
Yes, that's a very good, yes, that's good. So let's follow that reasoning this way. Let's keep 1, -1, 2, and that's perfect actually. So let's write it here. This was 0, 7 minus 1, 0, 6 minus 8. So this was how it was. You are proposing to write this one like this: 1, -1, 2, and you are saying to subtract row 2 minus row 3, right?
Yes.
Okay, we can do it. Let's do it that way. So we have 0 minus 0, nesumbi plus 0. Okay? That's even more elegant. So we can do it that way. 7 minus 6 is 1. -1 minus 8 is equal to what? 7.
So, Professor, you're not limited to when doing these reductions. You can either divide by a number, a row by a number, or you can subtract rows.
Yes,
so
yes.
you can do whichever it seems logical to you.
Of course, because we have the following: 2x plus z. This is equal to 2, and we have minus x plus 7z. This is equal to 3. What you are doing is that you are adding them together, and you are doing no mistake. So this is going to be x plus 8z. Yes, you can do whatever you said. You are correct. Okay, so you are doing this. Nobody's going to. These are linear equations. Nobody's going to say to you, no, this is not possible. It is possible. So
yeah, okay.
Okay. And you can also simplify it like this. But the procedure, so try to understand here. The procedure is good to make a leading one, following the procedure. But this is, you are already doing something equivalent to that. Then here, you can also simplify this to some degree by dividing by 2. You can get 3 minus 4, okay? So these kind of simplifications, they are legal. You can do them. So you are suggesting to do it this way. Then if we do it this way, we want to make, so this is 6 minus 8, and then you want to make this 0. How would you make this 0? You could say that row 3 minus 6 row 2. Would you agree with this?
Yes.
Yes, okay, thanks. So then we could do it right away. We can do it here. So we do 6 minus 6 times 1, we get 0 here. And this would be minus 8 plus 42. Minus 8 plus 42, what is it? It's 30 minus 8 plus 42. We get 34. Is it correct? 34. Okay. Then what we can do next is that we have a leading one here, and here we have a 34. We can simply divide them by 34.
34?
Sorry?
Is it minus?
No, I think it's plus. Wait, let me think. No, probably. Wait a second. So let me correct myself. We have row 3 minus 8 minus 6 times 7, right? I think it's minus 50 then, right? This is equal to minus 8 minus 42. No, this is minus 50. This is minus 50. But if this is minus 50, we can divide by 50 and we can write here a 1, okay? We can write here 1 because we can divide any equation here by 2, like as we have here, so we can write here 1. Then if we have here 1, so you can continue this path, okay? So let's go up this way. So now here we have a leading 1, and we want to make this 0. How can we do this? We can say row 2 star is equal to row 2 minus 7 row 3, okay? So we can have here, because we want to make this 7, 0. So let's write down, this is 0, 0, 1. And we have the following: 0 minus 0 is 0, 1 minus 0 is 1, 7 minus 7 it's 0. Okay? And then we can say that row 1 star is equal to row 1 minus 2 row 3. So here we have 1 minus 0, 1, minus 1 minus 0. We get minus 1, and 2 minus 2, we get 0, okay? So the leading ones are these here. And then it is obvious that the next step, what would be the next row? We're going to say row 1 star is equal to row 1 plus row 2. Would you agree? Because if we have these 2, we make this also 0. And finally, we get 1, 0, 0, 0, 0, 1, 0, 0, 0, 1. So this is the end result. So how do we read this equation? We read it like this: x, y, z. This is equal to 0, 0, 0. So what is the null space of A? What is the null space of this matrix here? So the null space of A, it's equal to the origin. It is a single point, okay? Which means that if we multiply these coefficients with any vector, it will be 0 only for this specific solution. Now, I want you to do this as a homework, the following exercise. So solve this one as a homework and submit this on the Google Classroom, assuming that B1 is equal to 1, 2, 3, and B2 equal to 1 minus 1 minus 2. Okay? So this is a homework, and you have to submit this one until next Thursday. So we solved this case for B equals 0, 0, 0. We found the null space is equal to this number. Now,
the A is that 1 minus 1, 2.
Sorry?
The homework.
Yes.
Which matrix should we have as A?
Yes, this matrix. This one.
Thank you.
Okay. So, if you forget the homework, you can always go over the recordings, and you can see what the numbers were. Okay.
Professor, so just to conclude, so the null space is the vector 0, 0, 0.
For this example, yes.
Yeah, for this example, where B is also 0,
Yes.
0. Okay. And not to be s'po du mu boj tepër, profesor, po veç edhe një pyetje.
Don't worry, no, please.
Do me thonë që kjo reduced row echelon form mundet mu përdor veç në square matrices, apo?
No, it's not only for square matrices. The first example we solved, it was a matrix which was 5 by 4, 4 by 5, right? 4 rows, 5 unknowns.
Yeah, it wasn't a square.
Okay, so that's good. So it's not only for square matrices. We always, actually, it is more educative. It teaches us much more details when it is not a square. Because when it is not a square, we have the chance of getting more free variables. If we get more free variables, we have this S and T, which should be like parameters multiplying a new vector, which has to be there, okay? So, yeah, it doesn't have to be a square matrix.
Okay,
now,
thank you.
Professor?
Yes.
Professor, I have a question.
Yes, please.
If the system of equations, which represent, each one represents a plane, from the system we end up in an equation which also represents a plane, do they all describe the same plane?
So you said that you have a system of equation which describes a plane, okay?
I mean, if each equation describes a plane, and we end up like in the first example we did in another equation describing a plane, would they all lie in the same plane, the solutions?
Let me think. Now, the first plane is a plane in a specific
I mean, we have graphically 3 planes.
Yes. Now, I was trying to answer this one. I understand your question. So let's visualize about this one in this way. So you have, if it is the 3-dimensional space, so let's think about initially. Let's pick up the first example. If you have 3 equations in 3 unknowns, because we can perceive 3-dimensional space easier. Okay. So let's assume we have this equation: 2x plus 5y minus z is equal to 2x minus 3y plus z, this is equal to 4. And then we have the third equation, which would be 3x plus 2y, this is equal to 6. Okay. So the first one, it's a plane, okay? It's a plane in 3-dimensional space. That's good. The second one is also another plane in 3-dimensional space. If this is plus z, let's say for a moment, this is also a plane. Now, if we have 3 planes in 3-dimensional space, we know that the intersection of 2 planes produces a line, the intersection of a line with another plane produces a point, so we get a unique solution, okay? But now, let's imagine that...
Professor.
Yes.
Ka mundësi të largohem sepse më duhet ikit e epoka për të bërë provimin e aptis.
Jo, do vishte epoka, se ishte epoka. Do vish tu.
Po, aty ku je.
Okay, po mund vishte epoka, patjetër. Okay. Yes, please. So now let's try to clarify this one. So now we said 3 unknowns, 3 planes, etc. Now, if you look at these expressions that I've written here, the third one is a summation of the first 2. Okay, we have 3x plus 2y, they cancel out 6. So the solution of this system is going to be a line, okay? The solution is going to be a line. And now, this line, it lies in this plane, okay? And then the question is, so I'm trying now, if you think in higher dimensions, you have a relationships of five variables, okay? And these variables, they lie in that initial plane, or that whatever structure is constructed in 5 dimensions. Then you give another relationship, which is going to be some structure, which is going to intersect probably these two surfaces. They intersect with another surface in 5-dimensional planes over 2 lines or 3 lines, you know, because maybe they wave around and they intersect twice. So you can assume that there is a structure like this, and you intersect it like in this way. So, and then once you are trying to find to determine the common points, because to find the solution of the system, you are trying to find the points which satisfy everything. Okay. So now the solution. I think what I gathered from your question is the following. The final solution that we're going to find, it is going to be a subset of the points that construct the initial plane. It's going to be the subset of the points that construct the second plane, and it's going to be subset of the third plane, and so on. Did I answer some part of your question?
Yes, I understand now.
Is it better? Okay. If I didn't do a good job, please, you can ask the question again, but I think I tried to clarify this one.
Professor, in the homework, what we have to do?
You have to find the solution of this system where the coefficient matrix is A and the result matrix is B1 and B2. So you solve B1, so you need to give 2 solutions. First, you solve for B1 with these numbers, and then you solve for B2 with these numbers.
So they are separated, okay.
Say it again.
So they are separated. We have to do 2 solutions.
Yeah, 2 solutions, yeah.
Okay, thank you.
You're welcome. Okay. Any more questions?
No.
Okay, so if you have no more questions, I can also add to you that this was all about chapter 2. Next time, when we will be together, we're going to start with chapter 3, where we discuss